All right, so now we're going to look at how acceleration affects velocity and position. So if acceleration is positive, then velocity is increasing. This is just like me saying if velocity was positive, then position is increasing. Because velocity is the derivative of position, it's the rate at which position changes with respect to time. The only difference here is that acceleration is the derivative of velocity. Okay? If acceleration is negative, then velocity is decreasing. Why is that the case? It's because acceleration is the rate at which velocity changes with respect to time. It is the derivative of velocity. Again, this is just like me saying if velocity is negative, then position is decreasing, using the fact that velocity is the derivative of position. If acceleration is 0, then velocity is constant. Okay, and if you want, we could draw little sketches just like we did in the previous. If I'm looking at my velocity function, time, and then velocity is a change in position over change in time. So let's actually just give little units. How about we're doing seconds and then feet per second. So I'm graphing my velocity function. Here's an example of velocity increasing. Velocity is increasing. And all of the slopes of the tangent lines to the velocity curve are positive. Right? Right? So if the slopes of the tangent line to the velocity curve are positive, acceleration has to be positive. Okay. Let's go ahead and do a little sketch for velocity decreasing as well as velocity being constant. Right? So velocity is change in time. Sorry, it's change in position over change in time. So for an example, we could use different units. How about we do hours and miles per hour. Here's my velocity curve that is decreasing. Velocity is decreasing. Its rate of change is negative. Oh wait, we have a special name for the rate of change of velocity. It is acceleration. All these slopes are negative. Negative slopes. Negative acceleration. If acceleration is 0, then velocity should be constant. How about meters per second? Here's my velocity curve. Say we are increasing, constant for a second, and then decreasing, and then increasing again. There are two moments here where the slope of the tangent line is 0. There are two moments in time when your velocity is 0. Okay, so we just did essentially the exact same work that we did in the activity before. What I want to now do is say, so we were looking at velocity curves and seeing, oh, if velocity is increasing, acceleration is positive. Those are equivalent statements. But what about position? Okay, so if acceleration is positive, velocity is increasing, comma, and position is what we call concave up. Oops, highlighter. Velocity is increasing, position is concave up. So concave up looks anything like part of a cup opening up like that. Let's draw a sketch. So I'm graphing my position curve now. So I'm looking at time and distance units, like feet. Time, like seconds. And here, my position function is concave up. When looking at this curve, can we see increasing velocities? If we can see increasing velocities, we know that their rate of change, acceleration, is positive. So where do I see velocity when I'm looking at the graph of the position function? Velocity is the slope of the tangent line to the position function. It's the derivative of position. So if I look at these slopes, you know, maybe right here we have a slope of about -2. Then we have a slope of, say, -1. Then we have a slope of 0. Then we have a slope of, say, 1. And then we have a slope of, say, +2. Okay, so if I look at the way those slopes are changing over time, they're increasing. A slope of -2, then a slope of -1, then a slope of 0, then a slope of 1, then a slope of 2. We have increasing slopes. What are the slopes? They're velocities. We have increasing velocities. Oh, so the rate of change of velocity must be positive. Oh, acceleration must be positive.
You're welcome. Yeah, you do.
Increasing slopes. Therefore, what are those slopes? They're velocities. Increasing velocities. Therefore, positive acceleration. Yeah? So, just 3 things. If acceleration is positive, velocity is increasing, and position is concave up. We'll get lots of practice with this, so don't worry. If acceleration is negative, then velocity is decreasing, and position is what we say concave up. concave. Oops, I'm sorry. Concave down. We just did concave up. My body, my brain left my body for a second here. Position is concave down. Let's draw a picture of a position function. Time units. How about hours? Distance units. How about miles? And here is concave down, like a frown. Here's your position function, and it is concave down. Now, if position is concave down, velocity is supposed to be decreasing. Getting my color here. Do we actually see decreasing velocities? Velocities are the slopes of the tangent lines to the position curve, and those slopes are decreasing over time. Let's see it. You know, here's a slope of, say, +2. So velocity is like +2 miles per hour at that moment in time. Here's a slope of approximately 1. We're going 1 mile an hour. Here's a slope of approximately 0. We're going 0 miles per hour. We're not moving at all. Our position is constant at that moment in time. Here's a slope of about -1, and so on, right? So over time, these slopes are decreasing. 2, 1, 0, -1, those numbers are decreasing. Those slopes are decreasing, therefore velocity is decreasing, therefore its rate of change is negative. We have a special name for the rate of change of velocity. It's the derivative of velocity called acceleration. Right? So decreasing slopes, therefore decreasing velocity. Therefore negative acceleration. Okay? And then lastly, if acceleration is 0, velocity is constant, and position has no concavity to it, your position function is linear. Position is linear. And that can be a line with any slope, including a slope of 0.
Yeah, sure. Let me show you something.
I'm going to graph position, so I care about time units. Oh, and I just caught a mistake over here for velocity. Meters per second. Okay, and so distance units, meters.
All of these functions are nice and smooth and continuous.
No.
So the contour line,
Here's my position function.
you'll always still be able to find a gradient vector as long as the gradient.
Sorry, 1 second. All right, so I can see my position function being linear here. The slope of the tangent line to that function is always the same number. Maybe here we feel like the slope is always 1. What does that mean? That means that velocity is always 1. In other words, velocity is constant. And the derivative of a constant is 0. What is the derivative of velocity? It's got a special name, and that name is acceleration.